In May of 2020, at a distance of roughly 149 astronomical units from the Sun, nearly 14 billion miles from home, something happened to Voyager 1 that had no clean explanation. Over the course of about 8 days, the spacecraft's magnetometer registered the magnetic field around it jump in strength by roughly 35%. At almost the exact same moment, its plasma wave instrument recorded the density of the interstellar material, pressing in from every side, rise by a nearly identical amount. Two completely different instruments, measuring two completely different properties of the space around the spacecraft, spiking together within the same narrow window. That alone would have been unremarkable. Voyager 1 had seen jumps like this before, small pressure fronts rippling outward from the Sun and briefly disturbing the interstellar plasma before fading back to normal within weeks or months, exactly as expected. This one did not fade. It kept climbing for more than a year, eventually peaking roughly 12 months after it began, and did not fully settle back toward its earlier baseline until nearly a year and a half after the disturbance first appeared, with elevated readings lingering in some form for well over 2 years afterward. Nothing in nearly a decade of prior interstellar observations looked anything like it. NASA scientists gave the event a name that undersells exactly how strange it actually is. They called it the magnetic hump. And now, in a research paper released this year using the most complete dataset available, stretching from the original 2020 event all the way through the middle of 2025, the scientists who first identified it are still not certain what it was or what it means. This is the story of that unresolved anomaly, why two respected teams of physicists have proposed two fundamentally incompatible explanations for it, and why the disagreement connects directly to a much bigger, much stranger question about exactly where our solar system sits inside the wider structure of the galaxy, and how much longer we might have before we drift out of the specific patch of interstellar space we currently call home. Subscribe now, because this channel breaks real, sourced science down properly, and this is one of those genuinely open questions where nobody, including the scientists closest to the data, actually knows the answer yet. To understand why this event confused researchers so badly, you first need to understand exactly where Voyager 1 was when it happened and how it got there. Voyager 1 launched on September 5th, 1977, built for an original mission lasting only 4 to 5 years, designed to fly past Jupiter and Saturn using onboard computers with roughly 68 kilobytes of memory split across 3 separate machines, running at a processing speed slower than an average pocket calculator built decades later. Engineers assembled it using slide rules and early mainframe computing, technology that looked almost primitive even by the standards of a few years afterward, yet reliable enough that the spacecraft is still transmitting data back to Earth today, nearly 50 years after launch. It swept past both planets in 1979 and 1980, gathering speed from their gravity in a series of carefully calculated slingshot maneuvers, and kept going long after its official mission ended, now traveling at roughly 38,000 miles an hour, covering close to 1 million miles every single day without pause, a pace that sounds enormous by any everyday standard, yet is still nowhere near fast enough to make a meaningful dent in the true scale of the galaxy. It is slowly leaving behind. In August of 2012, 35 years after launch, Voyager 1 crossed a boundary called the heliopause, the point where the outward pressure of the solar wind, the constant stream of charged particles released by our Sun, finally runs out of strength and gets stopped by the push of the interstellar medium pressing back from the other direction. That crossing made Voyager 1 the first human-made object in history to leave the protective bubble the Sun creates around the entire solar system and enter true interstellar space, the actual region between stars, rather than anything still shaped primarily by our own Sun's influence. For years afterward, the spacecraft sampled that environment steadily, sending back data that reshaped scientific understanding of what lies just beyond the Sun's reach, one careful measurement at a time, transmitted across a communication delay that grows a little longer with every passing year. And then in 2020, something changed that none of the existing models had prepared anyone for. Here's the detail that separates this event from everything else Voyager had ever recorded in interstellar space. In every previous disturbance the spacecraft picked up since crossing the heliopause, the pattern was consistent and predictable enough that researchers had come to treat it almost as routine. A spike would appear, usually triggered by a burst of solar activity, a coronal mass ejection or similar outburst rippling outward from the Sun, compressing the plasma, and briefly intensifying the magnetic field before everything settled back to baseline within weeks or months. That pattern held reliably across nearly a decade of prior observations. The 2020 event followed the same opening beat, an abrupt jump in both field strength and plasma density within about 8 days, exactly the kind of rapid onset scientists had already learned to recognize. But then it refused to fade the way it was supposed to. The field kept climbing for more than a year, reaching a peak around 2021, before finally declining back toward an earlier baseline level roughly a year and a half after the disturbance first began, with subtly elevated readings persisting for well over 2 years in total, a timeline utterly unlike anything in the prior record. Given how fast Voyager 1 was moving, that stretch of unusual behavior likely corresponded to several astronomical units of physical distance, an entire region of space with measurably different properties from everything immediately around it, extending far beyond anything a brief solar outburst should have been capable of producing on its own. Adam Sabo, the astrophysicist at NASA's Goddard Space Flight Center who serves as principal investigator for Voyager 1's magnetometer, had spent years describing these shorter, more typical disturbances using a specific metaphor, comparing the sun's outward pressure waves to a piston pushing rhythmically against the boundary of interstellar space and sending ripples outward that eventually faded back to nothing, the same way ordinary waves flatten out once their source stops generating them. The 2020 event did not behave like anything a simple piston could produce, no matter how the numbers were adjusted or reinterpreted. It was too long-lived, too sustained, too different from every prior pattern to fit comfortably into the solar explanation that had worked reliably for every earlier disturbance recorded during the spacecraft's time beyond the heliopause. Sabo proposed something considerably stranger, a genuine departure from the assumption that everything Voyager measures must ultimately trace back to our own sun. He suggested Voyager 1 might have drifted directly into a small, dense pocket of ancient interstellar plasma, a discrete cloud carrying a stronger magnetic signature inherited from whatever distant star or star-forming region originally produced it, sometime deep in the galaxy's past, long before our own solar system existed, in anything resembling its current form. If that explanation is correct, the sustained elevation in field strength and density would have nothing to do with the sun at all. It would instead represent a genuinely new region of the galaxy, a fossil remnant of some ancient stellar event that Voyager 1 happened to become the first human instrument ever to physically pass through and directly measure, a discovery made almost by accident, simply by being in the right place after nearly 50 years of travel. Here is where this story splits into open, unresolved disagreement, the kind of argument that is still playing out in scientific journals as recently as this year, with genuinely respected researchers weighing the same data differently. Not every scientist studying the Voyager readings accepted the interstellar cloud explanation. A separate team led by physicist Leonard Berlanga, working alongside colleagues including Nandlal Reddy Pogorelov, Lanjian, and Adam Sabo himself, argued instead that the sustained hump likely originated back at the sun after all, just through a mechanism nobody had modeled in enough detail to predict this exact signature in advance. Using detailed magneto-hydrodynamic computer simulations, essentially modeling the physics of the solar wind colliding with interstellar space across millions of individual calculations, this team demonstrated that a large-scale compression wave, generated by unusually high dynamic pressure in the solar wind several years earlier and propagating outward through the heliosheath before slamming into the heliopause, could reasonably reproduce both the shape and the roughly 2.5-year duration of what Voyager 1 actually measured. Their modeling traced the origin of that pressure wave back to conditions observed in the solar wind near Earth between roughly 2015 and 2017, meaning the disturbance that eventually reached Voyager 1 in 2020 had potentially been traveling outward through the solar system for years before it ever registered on the spacecraft's instruments. This solar explanation carries a specific, testable prediction. If a large-scale compression like this is tied to the roughly 11-year rhythm of the sun's own activity cycle, something broadly similar should eventually show up again, both on Voyager 1 and on its twin, Voyager 2, which is following a different path through interstellar space on the opposite side of the solar system. There is a paper published just this past spring that complicates the tidy solar cycle explanation considerably, without fully resolving the disagreement one way or the other. Researchers went back through the complete Voyager 1 magnetic field dataset, covering the entire period from the original 2020 hump all the way through the middle of 2025. 5 additional years of data collected after the initial disturbance faded, giving them a far longer baseline to compare against. The team, working with both Berlanga and Szabo, examined not just the broad shape of the disturbance, but the fine-grained texture of the magnetic field within it, a statistical property called intermittency. Essentially, how choppy and turbulent the tiny rapid fluctuations in the field actually are, moment to moment, well below the scale of the sweeping trends that first caught everyone's attention back in 2020. What they found was that after the disturbance settled down around 2022, that fine-grained turbulence largely disappeared, leaving behind a magnetic field that behaves in a smoother, more orderly, more mathematically simple way than the choppy, structured turbulence typically seen in the solar wind and in the heliosheath just inside the heliopause. That shift in texture does not map cleanly onto either original explanation on its own. It adds a layer of nuance that neither the ancient cloud theory nor the solar cycle compression theory had fully anticipated. The scientists studying this are being careful not to overclaim, and their language throughout the published work remains genuinely cautious. But the honest state of the research right now is that neither explanation has been fully confirmed and neither has been fully ruled out, leaving the question almost exactly as open as it was when Sabo first raised it years earlier. If you're the kind of person who wants the actual reasoning behind a headline instead of just the exciting part, that's exactly why this channel exists. So, like on this video tells me to keep making more like it. Now think about what is actually being tested here, underneath the specific technical disagreement over one particular anomaly recorded by one aging spacecraft. This question connects directly to something far bigger than a single unusual event from 2020. Our entire solar system is not sitting in some fixed, permanent location within the galaxy, frozen in place the way star charts sometimes make it feel. It is moving, carried along by the sun's own orbit around the galactic center, currently drifting relative to its immediate surroundings at roughly 16 miles per second, passing through a specific region of interstellar space called the local interstellar cloud, sometimes nicknamed the local fluff, a diffuse patch of warm, thin interstellar gas roughly 30 light-years across that our entire solar system has been moving through for an unknown span of time, likely tens of thousands of years by most current estimates. Astronomers are not even fully certain whether the sun currently sits comfortably inside this cloud or whether it may already be crossing into some kind of transition zone at the cloud's outer edge, bordering an entirely separate neighboring cloud. Researchers call the G cloud, a genuinely different pocket of interstellar material with its own distinct properties and its own separate history. Some analyses suggest the sun could fully exit the local interstellar cloud within as little as 1900 years, an eye blink on any meaningful cosmic timescale, barely longer than the entire span of recorded human civilization. If Voyager 1's 2020 hump really did represent a brief encounter with a small, discrete pocket of older interstellar material, exactly the kind of feature you would expect scattered along the ragged, uneven boundary between two neighboring interstellar clouds, then the spacecraft may have handed scientists an unplanned, accidental preview of exactly the kind of environment our entire solar system is destined to pass through in the relatively near cosmic future. It helps to understand just how strange this neighboring region of the galaxy actually is on its own terms, independent of anything Voyager 1 specifically detected. The local interstellar cloud is remarkably thin, containing roughly 0.3 of an atom per cubic centimeter, a density so low it would register as an almost perfect vacuum by any everyday standard. And yet it is still dense enough, spread across enough distance, to meaningfully shape the size and behavior of the protective bubble our sun projects around the entire solar system. Researchers studying absorption lines in the light of nearby stars have suggested the boundary of this cloud may sit only a fraction of a light year from the sun in certain directions, astonishingly close on a galactic scale, close enough that the sun could genuinely be considered to be sitting right at the edge of its own neighborhood, rather than comfortably in the middle of it. Other analyses push that boundary out considerably further, describing a single irregular cloud extending unevenly in different directions, with pockets and extensions that do not behave like a simple symmetrical bubble at all. That basic disagreement over something as fundamental as how large the cloud surrounding our own solar system actually is has existed in the scientific literature for decades, largely because no instrument had ever been able to sample the boundary directly from the inside until Voyager 1 finally arrived there in person, carrying instruments built in an era before anyone knew precisely what they might eventually find, decades before the phrase very local interstellar medium had even entered common scientific use. There's a detail buried in all of this that deserves its own moment of attention, because it reaches into something more human than the raw physics does, something about the strange patchwork nature of trying to do cutting-edge science with instruments never designed for exactly this purpose. Every measurement discussed in this video was gathered by hardware built in the 1970s, running on a radioactive power source that loses a small, fixed amount of usable electricity every single year without exception, a slow, mathematically certain decline nobody involved in the mission can stop or reverse. By the time the 2020 magnetic hump began, Voyager 1's plasma science instrument, the one tool that could have given scientists a direct, unambiguous reading of exactly what kind of charged particles were present during the disturbance, had already been dead for 4 decades, having failed all the way back in 1980, before the spacecraft had even reached Saturn, decades before anyone could have possibly anticipated needing that specific instrument for a mystery like this one. Everything scientists know about the 2020 hump instead comes from the magnetometer and the plasma wave instrument, tools that can detect that something dramatic happened and measure its strength and duration with real precision, but cannot directly identify the exact composition or origin of the material involved the way the dead plasma instrument might have, had it somehow survived long enough to still be operational when this specific anomaly finally arrived. Researchers are working around a permanent, decades-old gap in their toolkit, piecing together an explanation for one of the strangest things Voyager 1 has ever recorded, using instruments that were never specifically designed to solve exactly this kind of mystery, on a spacecraft that nobody in the 1970s ever expected to still be operational, let alone still generating genuinely open scientific questions 5 decades later. Questions serious enough to justify multiple peer-reviewed papers and ongoing international collaboration among researchers who were not even born when the spacecraft first launched. The spacecraft's fragility is not a hypothetical concern either. In November of 2023, a corrupted chip inside one of Voyager 1's onboard computers scrambled its transmissions into unreadable static, cutting off usable science and engineering data entirely for roughly 6 months, while engineers on Earth, working across a round-trip communication delay of nearly 2 full days, painstakingly diagnosed a problem in hardware built half a century earlier using documentation that predated most of their own careers. The team eventually traced the fault to a single corrupted memory chip and worked out a way to reroute the affected code into other working sections of memory that had enough spare capacity left to hold it, coaxing the spacecraft back into coherent communication in the spring of 2024. It was a reminder that every additional year of data, including the very dataset used to study the 2020 hump, is not guaranteed. Consider what that means for how confident scientists can be about ever fully resolving this specific question using this specific spacecraft. Voyager 1 is currently operating on borrowed time in the most literal sense possible. Its every remaining transmission a small, unearned bonus decades beyond anything its original engineers dared plan for. Engineers have already been forced to shut down instrument after instrument as the spacecraft's dwindling power supply falls below what is needed to keep everything running simultaneously, making increasingly difficult triage decisions about which remaining tools are worth preserving, and which ones simply have to go dark permanently with no possibility of ever being switched back on. Whatever data Voyager 1 manages to send back over the coming years represents an unrepeatable, irreplaceable resource, because there is no second spacecraft currently anywhere near this specific region of interstellar space capable of independently confirming or challenging whatever the instrument records next, and none is currently funded, designed, or scheduled to launch any time in the foreseeable future. If another magnetic hump event begins and Voyager 1's magnetometer has already been powered down by the time it happens, that data will simply never exist, lost permanently the moment the opportunity to record it passes by unobserved. So where does this actually leave us right now, at this exact moment in the ongoing research? The most recent published analysis, extending the intermittency study through the middle of 2025, represents the current edge of what anyone actually knows about this event, the absolute frontier of peer-reviewed understanding. It does not resolve the disagreement between the ancient interstellar cloud explanation and the solar cycle pressure wave explanation, and it was never really designed to settle the question outright in a single paper. It complicates both of them slightly, adding fine-grained statistical detail that neither existing model fully accounts for on its own, the kind of inconvenient nuance that tends to characterize genuinely unresolved scientific questions rather than tidy, settled ones. Scientists studying Voyager's ongoing data stream are continuing to watch closely for any sign of the pattern repeating, since a genuine solar cycle origin would predict something broadly similar, recurring roughly every 11 years, meaning a second comparable event could plausibly appear sometime before the end of this decade, assuming Voyager 1's remaining instruments are still functioning by the time it arrives, which is itself far from guaranteed, given the spacecraft's steadily shrinking power budget. If a second hump does eventually show up, closely matching the shape, timing, and characteristics of the first one, that would represent powerful evidence favoring the solar explanation, essentially closing the case through simple, repeated confirmation. If years pass with nothing similar recorded again, the ancient interstellar cloud explanation gains considerably more weight by process of elimination, becoming the more plausible option almost by default, rather than through any single decisive piece of new evidence. Step back for a moment from the specific magnetic field measurements and the competing research papers, and consider what this entire story actually represents in the broadest possible sense. A machine built nearly 50 years ago, running on components that predate the internet, personal computers, and cell phones, is currently sitting in a region of space so remote that a radio signal traveling at the literal speed of light needs the better part of a day just to complete the journey back to Earth, a delay so long it genuinely reshapes how the scientists working with it have to plan every command they send. On November 18th, 2026, at 2:16 in the morning Pacific time, Voyager 1 will reach a distance of just over 16 billion miles from Earth and become the first human-made object to sit a full light day away from home, meaning a command sent that day and answered immediately would still take 2 full days to complete the round trip. From that unimaginable distance, using instruments that were never specifically designed to solve the exact mystery they eventually stumbled into decades after launch, the spacecraft detected something genuinely strange happening in the fabric of the space between stars. a sustained structural disturbance that neither of the two best competing scientific explanations can fully account for even 6 years and multiple published research papers later. Whatever the eventual answer turns out to be, whether Voyager 1 briefly passed through the ghost of an ancient, long-dead star system's leftover material, drifting silently through the galaxy for who knows how many thousands of years before a human spacecraft happened to cross its path, or whether it caught the outer edge of a pressure wave sent rippling outward from our own sun across 14 billion miles of empty darkness, the fact that a single aging spacecraft could still, this year, be generating this much genuine scientific uncertainty says something remarkable about how little of the space immediately surrounding our own solar system we have actually managed to directly measure and understand, despite nearly 50 years of continuous effort and some of the most careful, patient science ever conducted by any research team on the planet. If discoveries like this one, built on real published research rather than manufactured mystery, are what you come here for, subscribe and turn on notifications, because Voyager 1 is closing in on that light day milestone later this year, and whatever data it manages to send back between now and then could add another crucial piece to this exact unresolved puzzle, arriving at a moment when the entire scientific community is already paying unusually close attention to everything the spacecraft transmits. Drop a comment with your own guess for what actually caused the 2020 magnetic hump, an ancient interstellar cloud left behind by some long-dead star system that vanished long before human civilization began. A delayed solar pressure wave, finally catching up with the spacecraft after traveling 14 billion miles through the emptiness of space, or something else entirely that nobody studying the data has proposed yet, some third explanation still waiting to be worked out by a researcher who has not even looked at this particular dataset closely yet. Because right now, the honest answer from the scientists closest to this research is that they genuinely do not know for certain, and they are not pretending otherwise in any of their published work. And share this with someone who assumes the space immediately surrounding our solar system has already been fully mapped and understood by now, nearly 50 years into the space age, well into an era when most people assume the big discoveries about our own cosmic backyard have already been made. Because the truth, according to the very latest research, is that a 50-year-old spacecraft running on a dying power supply is still finding structures out there that current physics cannot yet fully explain, with no clear end in sight to exactly how many more surprises might still be waiting in the data still to come. Thanks so much for watching today, and stay genuinely, relentlessly curious about what this aging spacecraft finds next.